Yes, hello. Yeah, let us start. Yeah, hi. So, last time I missed to discuss one of the interesting questions which I had given the class before that. So let's try that out today, and then we can proceed further. So 1 minute. So what was the question? Okay. Let us first, let me just mention the context in which this was given. So there was this problem, I'll just say old problem, and this was rather easy. It was the question was asking if this and so on. So you obviously see the pattern. Is this finite? Right? That is what the question was. And once again, to put it more concretely, we can say that what does it mean to say if this is finite? To put it very concretely, this means that if you define the partial sum, the kth partial sum as k till the kth term to be this. Maybe you can define it to be this. There are k plus 1 ones. If you define this to be the kth partial sum, so remember, when we are adding infinitely many terms, we are never actually adding infinitely many terms, right? We are basically adding finitely many terms, but we are adding more and more, and we are trying to understand what happens when you do that, right? So essentially, we are asking, are all SKs bounded above by some number, right? Is there some number? If you don't have to find the number, you have to just say that there is some number, okay, and so on. Obviously, if some number works, then bigger numbers bigger than that will also work. Okay, now all this is unnecessary for doing this question, but I'm just putting it like this because this will become necessary soon, so it's good to get used to it in simpler context places. Okay, so does everybody understand that this is exactly what the question is, right? We are asking, is there some number such that all the partial sums are less than that number? That's what it means to ask, is this finite? Okay, but obviously for solving it, we are just going to show that we're just going to compare this with some geometric series or some series which is finite, and so this will also be finite. Simple as that, right? So the answer to this was yes. This was a very simple question. The answer to this was yes. Obviously, the harder version of this question actually is, okay, if this is finite, then the next question which number theorists will ask, is this going to be rational or irrational? Is it rational? That's something that you guys can think about. Is it rational? Because all these things are rational, but then there are infinitely many, or in some sense, we are taking a limit. So that's just a very vague question. Is it rational? It's a good question to explore, and it is not easy to answer. But that was just the context. Now the actual question, maybe actual, was in some sense inspired from this, but also it's basically a question which was in one of the entrance exams. Yeah. So here we are looking at, so basically this is a portion of this. This series of all ones is a portion of this series, right? It is just a piece where you are only taking those numbers which only have ones, right? So that's one end of the spectrum where you take numbers which have only ones. And then the other end of the spectrum is, so if all ones is one end of the spectrum, then can anybody say what should the other end of the spectrum be? What should be the other version of this question? Where you don't have any ones, right? exactly. So that's the thing. So we are just going to take those numbers which don't have ones at all. So there will be numbers like this. We go from here till 9, then we don't use 10 because 10 has a 1, and then we can't use 11, we can't use 12, and so on. We'll go to 20, then you can't use 21, we go to 22, and like this we go till 29, and then obviously 30 also, but then we don't take 31, we take 32, and we keep going like this. Is it clear to everyone what this series is about? Okay, we are going to only add those numbers. We are only going to consider those numbers which don't have 1 in base 10. But you can forget about that. Just in the ordinary sense, we are saying don't have 1. Okay, but obviously we need to start in introducing symbols which will help us to better describe these things. And the symbol for this is, obviously you guys can break it down and understand, so I'm not going to explain it in details, but the symbol just is, this is just a sign of summation. This just means taking the summation, and you describe here, what are the properties of the numbers that appear in the summation. Okay, so n has no ones and 1 by n. So those n's which don't have ones, and just add them up. Okay, so that's the thing. So the question was, is this finite? So if we call this, yeah, so the question is just, let's not call it anything. Is this finite? That's what the actual question is. So that is just and this is again a part of the harmonic series. Yeah. So has anybody tried this? Has anybody has any ideas? Because yeah, or even some guess in the list. Yes, yes. So to just put it briefly, the question just says that we are just taking 1 by n, okay, but we are only considering those numbers. As you can see, there is some sort of a pattern here. We are only considering those numbers which do not have a 1 as a digit in it, right? And we are taking its reciprocal, and we are adding those numbers up, okay? And the question is, will this summation remain finite? Meaning that, is it bounded above, right? Or does it blow up? Does it become bigger and bigger than anything? Or is there something that bounds these things, these numbers, this summation, no matter how many of these you add? Okay. And all those words I'm saying that can be just said in one word called convergent. Is this series convergent? But we'll introduce that formally after we do sequences, which I plan to start today. It means we already started. So let's think about this question. This is a very relevant question in our context, and also I think it's an ISA entrance question also. So any guesses? Anyone has guessed anything? Okay. Yeah, a lot of numbers are getting lost. That is, the amount of denominator is becoming smaller and smaller, but you see, that also happens, well, you know it, but I'm just repeating it. It also happens here. If you take all numbers, so if you just take all numbers, so 101, 102, 103, this is infinite, right? Everybody, we all know that, right? This is infinite in the sense that this just becomes bigger and bigger. Okay. But what happens to this is the real question. So yes, it seems like it is finite, but then let me not even write anything as a guess, because it's very premature right now to say anything. I think from what we have said. So what should we, okay, what should be the way we can approach this problem? How we can start, how to start? We really want to solve this and in a sense that discuss it also that we understand the methods. How to approach? That's the question. And if you want to take that as a hint, then the idea, the point I'm trying to make here through this problem is that no new idea is actually needed. We will just be comparing it with a good old geometric progression kind of thing only. Just the methods that we have been using previously we'll be using here. Okay. And we have to do some sort of a comparison. Okay. So I'll just say, just write the two key points here, comparison. Sorry, 1 minute. I should. So the keywords here, and we will see this clearly, comparison, just only one, yeah, comparison with a GP. Now, what do I mean by GP here? Well, we know it, but my point is that comparing it with something like 1 r square, r cube, and so on, and r is less than 1. We know that this is finite. Yeah, this is something that we had shown. One second, sorry. So we had shown that if r is less than 1, then this series is finite, right? And no matter how many you add, it remains. If you can put it in a rectangle and so on, we had seen. That is what we are going to do. And this is what we have been doing even earlier, right? So that's what we are going to do. So in these kind of questions, when you're seeing that this series doesn't fit in any of the boxes that we have already done, we have any of the categories of series that we have looked at, it doesn't really fit in, like not in the factorial one, not in 1 by n square or 1 by n to the power something. It's not, it's a very, it's number theoretically, coming. So it's not, doesn't fit in, right? So we are going to use comparison, but in general, from this, just from what I have, what I understand, what my experience has been in these kind of questions, it is very important to know whether you are trying to prove it's finite or trying to prove it is infinite. That is very important to know. Okay, so let me write here, we are trying to prove it is finite. Just writing that very clearly. Okay, because see, we may be wrong and we may understand, we may figure it out if we are wrong. Okay, but one must go with the affirmative approach in the sense, otherwise these questions you will not know which side to compare, what to bound it with, and so on, right? So we're trying to prove it is finite. Obviously if we are wrong, we will hopefully know. So we will try to bound it above. We will try to use this is less than something, less than something, less than something, and this something is also finite. That's what we're trying to do. Okay. So yeah, let's think how we can group. What is the basis on which we can group the terms? Any ideas? How, obviously we're comparing, right? So we have to group the terms and then compare. So how should we group the terms here in this kind of series? Let me remove this. Maybe also this. How to group the terms? Based on what? Do we group it like, two groups of 2, 4, 8, that kind of thing, or do we group based on something else and then put an upper bound? So something like we had done one kind of grouping earlier, which was if you had something like and obviously to do this problem, it's very combinatorial in nature. So usually the other techniques of integration and so on, which you later learn, will also not be very useful. Okay, so this kind of problem you have to do it, based on the method. It's hard to quote a theorem. Obviously there will be some specialized result in number theory which will be do, but not that I know of. And yeah, if you keep going like this, so we had done some sort of a grouping to do this question, right? So how had we grouped this? Let's just write it. Just remind ourselves. Anybody remembers, or can? So we had proved that it is finite, right? We had proven it is finite, and we had done some sort of a grouping and comparing. Let's think about how we had done that. So we had shown that this is finite. We had shown that it never grows beyond a certain number, no matter how many terms you add. So we had put an upper bound, right? We had put an upper bound, right? So the way we had done it, I think, I mean, if you want to put an upper bound, is 1 by 3 square, right? So it's something like this is this group. 1 by 3 square is less than 1 by 2 square, and 1 by 2 square is equal to 1 by 2 square. And so similarly, now you get the idea from here to here, right? All of these are less than 1 by 4 square, less than equal to 1 by 4 square, right? 1 by 6 square is less than 1 by 4 square, 1 by 7 square is less than 1 by 4 square, like this. And similarly, from 8 to 15, you had grouped, right? And that way we had done. So we had grouped it in a certain way there, right? How should we group here? That is really what the question is. This kind of grouping will not work. You can think. Mm-hmm. Mm-hmm. Okay, n raised to n and n raised to n plus 10 raised to n and 10 raised. No. So that is what. So I mean, so you should put it in the way. So if you try to frame that in the way I am asking, then that's basically group it based on the number of digits. That's what you should say, right? I mean, yes, what you're saying is correct. So the basically what you're saying is group. So if I'm asking group it based on what, how should we group? So the idea is group it based on the number of digits, right? That's what you're basically saying, but in a more formal way. So group based on number of digits is the idea, on the number of digits. Because that's what, right? When 10 to the power n, you get 10 to the power n plus 1, you get all numbers, all n digit or n plus 1 digit numbers, right? So you're then looking there. That's what we're going to do. But yeah, so we're just trying to say it in a more colloquial manner, group based on the number of digits. Okay, so this means that we are going to form this group. We are going to take 1 by 3 to 1 by 9. Yeah, so what you're saying will absolutely work. I'm just doing the same thing. And then, so you group that because they are all 1-digit numbers. And then you look at all the 2-digit numbers. And that is also what the idea initially was said, I think, by Pragya, to say that it is finite, right? Because you're looking at the number of digits and where we're losing a lot of terms, and that's why, and so on. So you look at all the 2-digit numbers, and so that is this, and then you look at all the 3-digit numbers. So that will take some time. It will start from 200, and then there'll be a lot of skippings and so on in between, but finally it'll go to 999. And these are all 3-digit numbers, and so on. Okay, I mean, that's how this is a more natural way to try things. I mean, you won't suddenly maybe someone will. It depends on the way you think. People think. You can say, look at. So basically, you are partitioning the number line based on powers of 10. So if you remember, in some other questions, we had partitioned it, the number line, in some other ways for some purposes. So here, yeah, but this is a more natural way because just continuing the analogy of grouping and so on. Yeah, same thing, all same thing. So now, okay, now that's so good. Now, how do we do the comparison? I guess now it should be obvious, right? I mean, if you're going to compare, you should obviously compare it with the least member of that group, isn't it? In the sense that, or rather with the greatest member of the group, so that the least term, right? The least index term. So obviously you're going to compare it with half, but you can just compare it with one also. You can compare it with half, it will work. You'll get the right answer. You won't get the wrong answer. But I'm just going to compare it with one for simplicity. Okay. So if you compare it with one, then this is less than 9. Is that right? That's a very, very crude comparison. You can compare it with half. You're welcome to do that. You'll get 9 by 2. But I'm just going to compare it like this because I know it will not matter in the end. But you can do it by 9. You can write 9 by 2 also. So yes, yes. So just like, so when you group it, then you compare it, right? So the half is less than 1, 1 by 3 is less than 1, 1 by 4 is less than 1, and so on. 1 by 9 is less than 1. Right. And you see, the idea is just the same, right? So that's the way I'm trying to present the solution, or rather just saying that that's the way we should think. Okay. That it's not some different trick suddenly in this question. No, it's just the same idea of grouping and comparing. And this always, when you group, you will usually compare it with the least member of that group. Obviously, the least member is 1, which is absent here. So you can do 9 by 2 also if you compare it with half, half, half. But I'm just doing this for simplicity. So these are the ideas, when you want to show it's finite, right? So you'll group first and then compare. Sometimes you may have to do something more. In harder questions, you may have to apply some AMHM inequality and so on. So we can't say, okay, you have to do a more sharper comparison. But usually it will not be needed because we don't want the best bound. We just want a bound. Okay, so on. Okay, so now can anybody just simply continue the analogy and just say what should be in this one? Yeah, sorry. That's right. That's right. So then what should be this less than? So yeah, so you can just say 1 by 20, 1 by 20, and so on. And then how many numbers are there? That's a very, no, it will be less than. You can think about that because other things are less than. Other things are strictly less than, right? That doesn't matter. You can write equal to. It's not wrong. Yeah. Either way, how many numbers are there? So basically this comes, and that's very simple to do, but I'm just saying it in a way, how many 2-digit numbers, if this is too basic, then just please interrupt me and I mean, but there are two, basically we are looking for 2-digit numbers which do not have a 1, right? So we have, is that right? So we have 9 choices for the units place. You can have 0, 2, and so on. So 9 choices there. Just very silly, simple. Okay. And for this one, you again have 9 choices. Is that right? Because you can't have a 0. So there are 81 of them. There are 81 of them. There are 9 square of them. And if you're not happy with this, you can simply just count it yourself and check it. Okay. That is something that you should just verify. Okay. Oh, 8 choices, right? Yes. Sorry. That's right. So this will be 8 choices. Right. But even if you write a 9, it's not, you still get the right answer, but 8 is the right way to do. Yeah. So this is 8 into 9. So it's just, so I'll just write 8 into 9. Okay. Now it's just very, very simple, right? And also this 1 by 20, you can write 1 by 20 and you can write 9 by 2, but I will just do 1 by 10. Okay, because you see it's also less than 1 by 10. Okay. Just for simplicity, it won't really matter. And do it and anyway. So in any case, this is also again the same question. You guys should think about how many numbers are there. It's very simple. Okay, but the good way to do is by counting, by the multiplication principle, which we just doing on Sunday, right? So this is just 8 into 9 into 9. So that's 8 times 9 square by, again, you can write 200, but I just write 100 and so on. Okay. Work out the details. Work out the details. Okay, check for 4-digit, 5-digit, do all that. It's very simple, and complete the problem. Okay. So you have to complete it. If you want, you can write it and also show it to me. Okay. Try to complete it. It's very simple now. You can see a geometry progression evolving. But yeah. Okay. So if it is okay till here, I will continue to something else in the next thing. Okay. All right. So then let's move on. Okay. No, that's not enough, right? You have to now show, yeah, I mean, I think you understand that, but the point is that you now need to show that this plus this, obviously you know that, plus this and so on is also finite, right? Now we need to show that this and this and the next thing will be this and so on is finite. Is that right? We need to show this, isn't it? You're grouping and then comparing, and this is obviously finite because if you forget about the 8, then it's a geometric progression. 9 by 10 is the ratio. 9 by 10 is the ratio, is less than 1. You can finish it. Okay. So grouping and comparing, and it's so similar to the questions we have already done. That was my point. Okay. Okay. So that was the question. Now you can try to, so there are some variations which I would like to give, and please try this. Please try these things. It's you may feel it's very easy. It is easy, but just work it out. Okay, write it out and so on. There's a variation to this, and one variation is that summation over all thing, no, let's say no zeros. So those numbers which don't have a 0, or those which don't have a 1, all of them, you can just work it out. Okay, this is simple, very simple. It's in fact the same thing, but work it out. And then here we are summing over those which no ones and no zeros. Work it out, very simple, 1 by n. Okay, write it out and expand it and write it out and just work. Same method, exact same method will work. But here is the generalization which I just thought of. So that question was just a contest question. But this is a generalization which I thought of and I have not found it anywhere. So maybe I will. But I think it is true. I was working it out and it's true. So now we want to look at. So again, expand it out, and so this is hard. This is a little hard. Okay, so you may, if you just try these two, it's just a bonus for those. But you can think about this. Should think about this. Here, we are looking at those numbers. We are taking 1 by n, but only looking at those numbers. N has at most n to the power 10 ones. Okay. So it can have ones, but it cannot have more than 10 to the power 10 ones. This means that in the beginning, the series would look exactly like, you see, we will have everything. And because it can have 2 ones, 3 ones, and so on, right? After a very long time, after a very, very long time, there might be a problem. Till here also, it will be okay. After that, those numbers which have 10 to the power 10 ones, those numbers we will not be taking. So we are, well, you may feel we are only taking away very few numbers this time. So is this finite? Okay, so is the below finite? It's a challenge question. Try it. Okay, if you want. I will discuss this at some point. Maybe not. I'll discuss this. I'll skip a few weeks and discuss this because I just want us to be more familiar with these methods. Okay. So you could just note it down maybe. And let me just, before moving on, I think something is very important to this, just a slightly meta point. Okay, just so there is this thing, right? So we know that if you take this series, take this series, this is infinite. We know that this is infinite. But we had seen that if you slightly enlarge it, if you slightly increase the denominators, what do we mean by slightly increase the denominators? In the following way. If you make, instead of 3, you make 3 square, and instead of 4, you make 4 square, and so on. This is finite. We had seen the method. I just basically we reviewed it also. And there are many other ways to see this. Okay. The point I want to make, and also today we will also apply the last time's condensation technique here as well. We'll review it gradually and do it. Basically, what I want to say is that this harmonic series is like a very balanced one. It's like on the edge. It's like a tree. It's like a tree, right? A tree is like connected, but it gets disconnected very easily. If you just remove one edge, it becomes disconnected, right? This series is also like that. It's on the edge. That's why it's of central importance, and you can see all over the place in mathematics it appears. It appears. But the point is that, see, this series, the harmonic series is finite, but if you slightly increase this, then it becomes, sorry, the harmonic series is infinite. And if you slightly increase the denominators, then it becomes finite. Okay. We also see this, we have also seen this phenomena just today, right? From the harmonic series, which is infinite, which becomes bigger and bigger than anything, we kind of just removed those numbers which don't have 1, right? Now you see, yeah, which don't have 1. Now you see, there are so many numbers that have, which don't, so I mean, there are so many numbers which don't have 1, right? Like if you have the first, if we just saw that, right? If you just look at the 2-digit numbers, there are 99, there are 92-digit numbers, right? Out of that, 81 of them don't have 1s. So it's a rather big ratio, right? There are many of them which don't have 1. So what we took here, what the series that we looked at, no 1s, right? It's not that we have, no, we have reduced, we have not taken away too many terms from the harmonic series, right? Like out of 90, we're just taking away 9 terms. And out of the next 900, we will be taking away maybe 100 terms, right? Something 81, something like that, right? We didn't take away many terms because so many numbers are there which don't have 1s, right? 1 doesn't appear all the time. If you just think about, right, compared to the number of 2-digit numbers, number of 3-digit numbers, those which don't have 1s is rather small, but still this became finite. We just saw that. And if you try out the generalization that I gave, you will be even more surprised that that is also finite. You see, there we are not even taking away, what we are taking away is even lesser, right? We are allowing those numbers which have 1s, which don't, we are not allowing only those numbers which have more than 10 to the power 10 1s. Other than that, we're taking every number. Still that will be finite. So you see, the harmonic progression is on the edge. Okay. So it is, or the harmonic series, or not progression, what am I saying? HN is on the edge. It's really on the edge. Okay. So this phenomena is being enforced here. It's being in, okay, just give me 1 second. I have to plug in the charger. And these problems are basically enforcing that phenomenon. Okay. And as you do more, then later on you can so there are some open problems also related to HN on the edge. Okay, there are some quantified versions right now. We don't have yet the language to quantify it. We are just basically seeing glimpses of it in various places. Okay, but it's good to have this. So later on, you can actually ask serious questions. But let me show you another, you know, appearance of this phenomena as on the edge. Okay, and that is the following: fix epsilon bigger than 1, or for the time being, let us just take um, k equal to 0. Very small. Okay, I meant bigger, slightly bigger than 1. Obviously, if less than 1, this is what I'm taking the k to be. It's just bigger than 1. Okay. Then the question is so that's what the k is. K is simply that I'm just not writing it because it's a big number. It's small number with big expansion. You see, is this finite? So it is just slightly, we are reducing. 1 by 2, we are only slightly reducing it by making it 1 by 2 to the power 1.0001. Only slightly increasing it. Sorry, only slightly decreasing it. Yeah, right? The number 1 by 2 is decreased to this. Question is this finite? Let's think. And this question can be answered very simply, can be also answered using integration and other methods. Okay. But for the time being, let's not forget about all that and do this. As you've seen, there are combinatorial versions of this like this, which rather have to be done the way we did it almost. In any case, yeah. This is what the question is this finite? So let's think about this. Can we do some sort of group and compare for this question, or what can we do? So the answer is actually very simple. Okay, and the method is the exact group and compare. Exact group and compare that worked for, I just call it S2, that worked for this will work here. Please try it out. The exact thing will work. Okay, let's actually see it. Let's actually see it, right? I mean, what are you going to do if you, okay, if we just do the same thing, but we'll also see this through an application of the condensation method. Okay, I just wanted to show another applications is slightly more advanced for the time being. So we'll just see this one as a consequence of that. Yeah, so let's just see. So yeah, I mean, let's just see, meaning you guys can tell me how to do it, because I've just said the exact way we did the group and comparison for S2 will also work here. So okay, by S2, I should not call it S2, maybe I should just call it some E. Not S2, because S2 might suggest that it's two terms, some E. So essentially, we have to just repeat the same thing. Right? Just the 2 is replaced by K, but then we have to see the consequences. That's important to see if it actually will work in the end. Yeah. So how do we? So just the same thing, right? Just the same thing. We're just going to group this, and then we're just going to say, okay, this is less than 1 by 2 to the power k plus 1 by 2 to the power k. Okay. Then we are going to take, I missed the 7, and this is less than 4. I'm just writing it directly. Okay, now 4 by 4 to the power k, it's just the same thing. No difference. Yeah, maybe also boring. Now again, there are 8 terms here. So this is 8 to the power k, and so on and so on. Literally nothing has changed. Let's just finish the details. That's it. Yeah, we should do it. So here it becomes 2 by 2 to the power k. I mean, just write it there only. See, just same technique works. So this is just same thing. You have grouped it, and now you see simple. It becomes k minus 1, right? This becomes k minus 1, right? This becomes 8 to the power k. We just bring the 8 down and so on. Now you see this is again a geometric series, right? Again, you can work out the details. It's essentially just, if you take this to be your R and it's less than 1, why is it less than 1? Because k minus 1 is positive, all right? You can just work out the details, okay? This is simple. K minus 1 is positive, so it's less than 1. This is R, and this is R square. This is the square of it, and so on. So it's going to be finite. Just the same thing. One may have just spotted it there only, right? When we were doing that. So yeah, it's finite. It's bigger. It will get bigger and bigger as you reduce the k. This summation will become bigger and bigger, but it will remain finite. Obviously, right? It remains finite. For any k, it will remain finite. But as you decrease the k, the summation will become bigger. And it will become infinity if you put k equal to 1, which is, this is k equal to 1. So that's really on the edge, okay? For any k, so this is, so as you can understand, this 1.00 whatever, it's not important here. K bigger than 1 is important, not equal to. We do not allow equal to. K has to be bigger than 1, and this works. Okay, just the same thing. So now we have seen a proof of this, so maybe we won't enjoy the condensation technique here, but let me still nonetheless just show an application of that. Okay, because this group and compare is a good method. Sometimes it gets convoluted when the question is, one can easily convolute this question with logs and so on, and then it becomes messy to apply this technique. So are there any questions? Then we'll try to apply the previous day's thing again. That's the goal. Okay. The condensation method to discuss this thing. Okay, so let's move on. Okay. Yeah. So let's about this condensation method. So this is, see, basically condensation means grouping, right? The condensation method was basically that we just saw that this grouping and comparing technique is appearing all the time, again and again. So we said, yeah, let's just apply grouping and comparing on an abstract series, A1 plus A2 plus A3, and see what we get. And this is what we got when we applied that grouping on powers of 2s. Okay, so this is really nothing. It's not something which is suddenly a very profound thing. It is just trying to abstract the method and try to apply it in general. And so you apply it once, and then you can use it in many places. Okay, but let's just state what we had got. Then you can go back and try the proof if you do. What was the condensation method? So there was a first criteria, and that will bring me to also the second question, which I had asked last time, which we'll discuss after this. The first criteria was, okay, assume that this is decreasing or non-increasing. we had to assume that the series is going down, down. Okay. This was the assumption. This was the assumption, hypothesis. Under this assumption, we said that A1 plus, and also these are all positive. That is that is important, let's say. Okay. Just keep it for the time being. I think it's not, anyways. Yeah. Then we said that this, and please just work it out if you don't know. Just ask me if you don't, if you've forgotten. Just try it. Okay. This is finite if and only if. So again, this is just, you can keep in mind just some examples, 1 by 1 by 1 square, 1 by 2 square, 1 by 3 square. Please keep that example. You can keep r square, and there's so many examples we know, right? This is finite if and only if, okay, we grouped and compared, and so we now only end up with the powers of 2's, 2a2, 2 square, a2 square, which is a4, basically, I mean. So we basically need to only look at, it's a fantastic result. Okay, it's saying that we need to only look at those terms which are powers of 2's. Okay, and it's an if and only if thing, so it works both ways. Okay, 2 to the power 4 a, 2 to the power 4, and so on, right, is finite. And again, as I said, this is nothing new. You just apply that grouping and comparing once again. Again, as you can understand, the decreasing was important. So you group this, you say that, no, this is less than 2a2, then a4 to a7 is less than 4a4. You see, it's just the same thing. It's just, it looks almost just very simple, very simple. That's because we spend a lot of time rather on those simple things. That's why. Otherwise, this is usually introduced. Well, formally, it's yeah. Anyway, when it's introduced, if it's introduced directly just as this, then it might look a little, oh God, what is this? Okay, but now we know that it's rather simple. But please just work it out again. Okay, so it's a important thing. This is finite if and only if this is finite, which we see. What this means is that if this is infinite, then this is also infinite. So I could rather replace this by infinite, isn't it? Because I mean, if this is finite, then this is finite. So if this is infinite, then this is infinite. Also the other way, so it's just the same thing. I mean, either both are finite or both are infinite. It's just, okay. Very interesting method. Sometimes just this is like a lifesaver sometimes for problems and these kind of things. This is, I mean, formally Cauchy is attributed to this, though I don't like to use these names because, I don't know who really invented it, whatever. Okay, this is the records and such. So in any case, it's called the Cauchy CC, yeah? Cauchy condensation method. Let us try to see how we can use this to do what we just did about that formulaic series, the 1 by n to the power k. So in those spaces, you can apply this thing, right? No, you should never use this. You should never use this directly in an undergraduate exam. Okay. You should use the method, but then the method, right? So the method, and then you could, if you just basically just mimic the method of the proof that you use, and we should not be scared of that, right? We should just work it out once and for all ourselves. Take time and work it out, and if you get stuck, just then ask. Otherwise, work it out, and then you'll never be able to. And you can almost see this, right? This is just the group and just the grouping thing, right? It's just that we did, but just work it out. We had done this in class, but work it out yourself, then only you will see this. And yeah, and just ask next time if, or yeah, write it and show it. So, but we are just going to use it because I mean, we are doing it in a certain way, right? It's going one step at a time. So how do we see this? So we just write application. Okay. So you put epsilon bigger than 1, or rather k bigger than whatever else, epsilon bigger than 1, and then you see, then what were we interested in? We were interested in the phenomena that epsilon, this h, this harmonic thing is on the edge. So this, we want to check if this is finite. Is that right? We want to just check if this is finite. You see, this is what this is the A1, this is the A2, and so on, right? This is the A3 and blah blah blah. Right? Or maybe I should call this A2 and I'll just add a A1. You know, that is just for synchronization. Whatever. So, okay. So you see, we want to show if this is finite, but if you apply this method, then what do you get? Okay, so if this is finite, if you want answer to that, that is the same as answering this one, if this is finite. Okay, so we can just mimic the proof. Right now, just use this. Don't think about, okay, how am I going to mimic the proof? I'll get confused. No, it's okay. Right now, you just quote it. As you get more mature, just as doing these things, then we'll say, we can write it. Then you can easily write it. Over time, it will come. Okay. But try to work out this once, and right now, just try to just use this. Okay. So you see, if we apply this, then what are we going to? We're going to now write this series, right? What is this series? What is the second series? For this if this is the first series, you see, it's very simple. It is just, you see, 1, and then we have 2a2, right? So we will have 2 times 2 to the power epsilon, and then that's the magic here, 2 square a2 square. So that a2 square is this, a2 square a4 is this, right? That's what it is. That is 2 to the power 2 epsilon. Then you see, we're going to get 2 cube a8, right? The 8th term. That's just 2 to the power 3 cube, 3 epsilon, 2 to the power 3 epsilon, and so on, right? This is exactly what we had got when we were doing it, but right now we just, so I'm saying that this is method and that grouping thing is exact same, but sometimes this is more convenient. I mean, it will at least help you to decide whether the answer is finite or not. Then you can just mimic the proof and write it, so on. Okay. In any case, now we know now what is this. So it's the same as, so asking if this is finite is the same as asking if this is finite, and this is obviously finite because again, that's what we just did. You see, this just becomes, you see, it becomes 2 times epsilon minus 1, and this becomes epsilon minus 1, 3, and so on. And so it's just, this is the ratio, and it's a geometric progression. And since epsilon is bigger than 1, epsilon minus 1 is positive, so r is less than 1. This works, same thing. Okay, it's rather redundant, okay, in this situation, but yeah, I don't want to discuss the complicated examples right now, so we're just discussing this one. Okay, right. So let us move on. For those who know, for those who are comfortable with logarithms, I don't have the time today to discuss it details. But for those who are comfortable with logarithms or know it at all, try to answer this. Is 1 by log n, I should rather just say, is 2 log 2 plus 3 log 3 plus 4 log 4. I will just review logarithms once very briefly, and from a better angle and from a different angle. Okay, we will see. But for the time being, for those who already are comfortable, should try this. Is this finite? Okay, maybe you can think about this, what happens in this. And you can use this method here. try to just think about it and see what you get. Okay, that's an interesting question. Right. Okay, so now let us note it down. The next we are going to ask again a question about a general series when it is convergent. What are the necessary conditions? What is needed? Definitely needed. May not be sufficient, but definitely needed for convergence. That's what we're going to ask. So I suppose noted it down. So let's move on. Right. So we had seen this. So let all the terms be positive. Okay. So this just means all terms positive. And we wanted to understand, yeah, we wanted to understand necessary conditions, or rather I should just say simply if this is finite. So again, we are slowly going into asking questions about general series. Okay, if this is finite, then we had seen this AI has to go to zero. It has to go to zero. If it does not go to zero, then you are doomed. This we had seen, right? And what this means exactly, that's what we will, that's the next thing, limits of sequences, which we'll do. Okay. So here basically we are motivating that, right? We came from very simple questions and now we are into, to ask on the series, the nature of the sequence needs to be studied, and we'll go into sequences via that and we'll rigorize the process. Okay, but roughly this is making sense that the terms should go towards zero, so on, so on. Okay, but this was the second question. Okay, this was the question. If this is finite, then yeah, just give me 1 minute. I will finish this now, 2 minutes. If this is finite, then should this be, or rather is AI eventually, so eventually is important here, means after some point, eventually, because obviously initially you can do whatever you want, right? Eventually decreasing. Has anybody thought about this? So you see, initially I had said that the answer that it is true, but then I backtracked and I thought, and I think it's not correct. Has anybody thought about this? If you look at, yeah, has anybody thought about this? If you look at some examples, right? If someone has thought, then just interrupt me, okay? But if you look at examples, it's decreasing. Look at other examples. Certainly it is not sufficient, because we know that the harmonic thing is decreasing, the terms are decreasing, but it doesn't go to, it's not finite. But if it is finite, then should we need that the terms should decrease? That will be the question. So what was I saying? Yeah, 2 square, 3 square, 4 square. You see, this is also decreasing. All the things we have met so far. I mean, even if you go and look at this 1 by 1 factorial, 1 by 2 fact, this is also decreasing. So is this always true that if your thing is finite, then it should be decreasing at least eventually? So x to the power n wala thing, x to the power n by n factorial summation. I had given 100 in the mock test or whatever. That this is also decreasing after some point. We had shown that. So is it always true? Is it true? That's the question. Has anybody thought about this? This basically translates to a question in sequences, and those will be the motivations for us to study sequences and combinatorial properties and number theoretic properties. Sorry, analytic properties. Number theoretic properties later, maybe. After some time, means after a point, yeah. So there is some n such that after that point, maybe after n equal to 100, so the sequence stabilizing first, and then after that it's going down. So we know that it should go to 0, but does it mean that it should go down? Just think. No, right? It's not true. So this is not true actually. So that was a blunder I was making. So it is not true. Now it's a task for people to think of an example. So think of a series, think of, so this is, just try it out. Think of a series which is finite, but the terms are not decreasing. After any point, you look at, you check after a million terms, still you'll find there is an oscillation. But still it's finite and still it's going to zero. Terms are going to zero and the sum is finite. But the terms are not. So the most naturally occurring sequences seem to be all decreasing, but there are examples where it is not. Think of an example. And it's just a very simple, you can just make a very simple contrived example is the hand map. Okay. So yeah, that's it. Today, there we have some questions and we try them. Next time I'll also try to chip in some more easier questions. I didn't prepare that today, but already we have questions to try. Okay. So just note it down. That's it. But please try these things. If you try, spend time, then you can take more out of the class. Okay, okay then. So I'll end the meeting. Should I? Yeah, everybody has noted it down. Okay. So yeah, let's end it.